Now let's talk about the theorems, where which we said few of the theorems we are covering upon this particular class. So let's understand first the superposition theorem. It is used to find the solution to networks containing two or more voltage sources. The current through or voltage across an element in a linear bilateral network is equal to the algebraic sum of the currents or voltages produced independently by each source. I'll explain this point once again to the next slide, and that will be the main statement for the superposition theorem. For a two-source network, if the current produced by one source is in one direction, while that produced by the other is in the opposite direction, through the same resistor, the resulting current is the difference of the two and has the direction of the larger one. This is one of the conditions when we are taking individually sources where which the direction of the current are in the opposite to the same resistor, then the resulting current is the difference of the two, and the direction should be taken for the larger value of the current. If the individual currents are in the same direction, the resulting current is the sum of the two in the direction of the current. So this is vice versa for that particular previous condition. The total power delivered to a resistive element must be determined using the total current through or total voltage across element and cannot be determined by a simple sum of power levels established by each source. Now, how to apply a superposition theorem to a linear network? So for applying, you have certain conditions to need to be followed up. Replace all other independent voltage source with short circuit, thereby eliminating difference of potential, that is V is equal to 0. Internal influence of idle voltage source is 0. So this is one criteria for applying the superposition theorem, making it as a short circuit, and replace all other independent current source with an open circuit, thereby eliminating current, that is I is equal to 0. Internal influence of idle current source is infinite. Let's have the proof for the superposition theorem. These are the few of the conditions, and to apply it as well as few of the conditions for the superposition theorem, like if there are current produced by the same source when it's connected in the different meshes, and when it is in the opposite direction or to the same direction, and how the open circuit or how the short circuit have to be maintained. And this is a superposition theorem where which I'll repeat the statement once again. In any linear network containing linear impedances and energy sources, the current in any element is the vector sum of the currents that are separately caused in that element if each source of EMF were considered separately. Of course, all other sources being replaced at that time by their internal impedance. It means we need to find out the current through the common impedance. If you see this is a linear network circuit where which we have used the two sources as an E1 and this is an E2. Two meshes, this is mesh 1 and this is mesh 2. And the direction of the current, or in this direction, this is on I1. In this particular mesh is I1. And this second mesh, we have the current as an I2. And we have specified very clearly the direction of the current. So using, seeing this particular two direction current in two meshes, the current through this particular common impedance will be nothing but I1 plus I2. So, to obtain the superposition theorem, we will be following few points. The first is, imagine that the EMF source E2 is removed, considering its internal impedance Z2, and let I1 be the current in Z3 due to E1 alone. So if you say that for the first condition, we have removed this particular energy source E2, considering its internal impedance Z2 into the circuit, and I1 be the only current produced because of the E1 which is flowing through the resistance value Z. And for the second time, what we will do is we will remove this particular energy sources E1, but considering its internal impedance Z1, and let I2 be the only current flowing through internal impedance Z3 because of the source E2. It means for two conditions, like the first is E1 we have to remove, considering its impedance Z2, and because E1 is removed, there is only current flowing through the Z3 is I1, that is because of E1. Second is we will remove this energy source E1, considering its internal impedance Z1, and I2 be the only current flowing through Z3 because of the E2. These are the two first following points which need to be followed up. It means the earlier it was I1 because of E1, second it was I2 because of E2. So the sum I1 plus I2 is a current through Z3 when both EMF sources are operating. So what we need to find out is, we need to find out the current through the common impedance, and that is nothing but I1 plus I2. So we need to have the solve it, and we will say that how the theorem can be proved. So what we need to do is, we will take this particular circuit, or this figure 11 as we labeled it. This is mesh 1 and mesh 2. In the mesh 1, the current is I1, and this is the direction of the current in mesh 2. Label it as an I2. This is Z1, this is Z2, this is Z3, this is E1 and E2. So what we need to do is, to know the value of I1 plus I2, or I1 and I2, we need to apply Kirchhoff's voltage law to each meshes independently. Now we apply Kirchhoff's voltage law to this mesh, considering only this mesh. So Kirchhoff's voltage law is nothing but summation of product of all the currents and internal impedance or impedances should be equal to the summation of all the voltages in this particular mesh. It means, how we can get the equation? We can have the equation saying that I1 into Z1 plus, what is the current flowing through the Z3? It is I1 plus I2. So I1 into Z1 plus I1 plus I2 into Z3 should be equal to E1. So this is how we get a Kirchhoff's voltage law equation, applying it onto the mesh 1. Similarly, what is V2? V2 is nothing but E2. So E2 should be equal to I2 into Z2 plus I1 plus I2 into Z3. So these are the two basic equations. Here you can see it. By rearranging, or by taking I1 as a common, so E1 will be coming as Z1 plus Z3 into I1 plus Z3 I2. This is labeled as the first equation. If you see on the second, E2 will be equal to Z3 I1 plus Z2 plus Z3 into I2. So these are the two equations. Now by solving these two equations, to get the values of I1 and I2 independently by a mathematical expression, so we can have the value of I1 as an Z2 plus Z3 into E1 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1 minus Z3 E2 by Z1 Z2 plus Z2 Z3 plus Z3 Z1. So this is how we get the values of I1 and I2, and whereas I2 we got it as an Z1 Z3 into E2 divided by, please observe this denominator, we'll get into the same form. So Z1 Z3 by E2 into Z1, Z2 plus Z2, Z3 plus Z3, Z1 minus Z3 E1 by Z1, Z2 plus Z2, Z3 plus Z3, Z1. So we got the current because of EMF E1 and EMF E2 as I1 and I2 in equation as shown in equation 3rd and 4th. So what is the current through Z3? It is nothing but the summation of both the currents I1 plus I2. So if you add up equation 3 and 4, we'll get it as an I1 plus I2 is equal to Z2 E1 plus Z1 E2 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1. So let's remember this equation number 5. Okay. And now what is the condition? The condition is first we will be removing E2 and then we will be removing E1 and we will find out the new current which is flowing through the common impedances in Z. So imaging this particular circuit diagram, now the E2 is removed. This is the first condition. Now let's have what is the current through the Z3. Now when E2 is removed, the new network circuit can be seen in this manner. So here we have removed the E2 but considered its internal impedance as in Z2 value. So we will be having Z1, Z2 and Z3, 3 resistance or impedances, and this is, in fact, what is impedances? Impedances is nothing but a joint effect of resistance and reactance. And what is again reactance? Reactance are nothing but a resistance produced due to the any of the components, like resistance, it can be capacitance, it can be inductance. Like the resistance produced due to a capacitor can be called as a capacitive reactance, and the resistance produced due to the inductance can be called as an inductive reactance. So this reactance plus the resistance can be called as a total resistance or can be called as an impedance in the circuit. Now we have removed the E2 and considered its internal impedance in Z2. So this is how the new circuit can be drawn in, and the same, the direction of the current is both in the same as similar to the main diagram, main circuit circuit. So here we have labeled it as a new current as an I1 dash, and this is an I2 dash. Okay. So now let I1 and I2 be the current in two meshes respectively. Now you apply the Kirchhoff's voltage law to this particular new circuit diagram, figure 12 as we labeled it. So how the equation comes? This is an E1, right? So V1 should be equal to what? I into R. So E1 is equal to I1 dash into Z1, then plus what is the current flowing through this particular common impedance? This is I1 dash and I2 dash. So I1 dash plus I2 dash into Z3. So the equation for the Kirchhoff's voltage law for the mesh 1, it comes like E1 is equal to I1 dash into Z1 plus I1 dash plus I2 dash into Z3. Similarly, applying Kirchhoff's voltage law for the mesh 2. Now, do we have a source over here E2? No, we have removed. So this comes like 0 is equal to, what is the current in this particular mesh? This is an I2 dash. So 0 is equal to I2 dash into Z2 plus what is the current through this particular branch? I1 dash plus I2 dash. So plus I1 dash plus I2 dash into Z3. So these are the two equations. If you rearrange, then you can see in equation number 6 and 7, E1 is equal to Z1 plus Z3 into I1 dash plus Z3 into I2 dash. And the second equation comes like 0 is equal to Z3 I1 dash plus Z2 Z3 into I2 dash. So by rearranging, we can get equation 6 and 7. And now mathematically, if you solve this equation 6 and 7, we'll get I1 dash as Z2 plus Z3 into E1 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1, and I2 dash as Z3 E1 by Z1 Z2 plus Z2 Z3 plus Z3 Z1. So these are the two equations, I1 dash and I2 dash. Now, what is the second condition? Second condition is, first we will remove the first EMF, the first energy source as an E1. So here you can see in the new circuit diagram called figure 13, E1 is removed. So if you remove E1, considering its internal impedance Z1, and we label the mesh current as an I1 double dash and this particular mesh 2 as an I2 double dash. So this is Z1, Z2, the common impedance for both the meshes are Z3. This is mesh 1, mesh 2. The current in the mesh 1 is I1 double dash and the current in the mesh 2 is I2 double dash, considering but only energy source as an E. Now apply Kirchhoff's voltage law to again mesh 1 and mesh 2. So what is the answer? What is the equation? Here there is no source, so 0 should be equal to I1 double dash into Z1 plus what is the current flowing through this particular common branch is nothing but I1 dash plus I2 double dash, I1 double dash plus I2 double dash. So for the mesh 1, the equation comes like 0 should be equal to I1 double dash into Z1 plus I1 double dash plus I2 double dash into Z3. If you rearrange that, so this can be written as Z1 plus Z3 into I1 double dash plus Z3 into I2 double dash. Similarly, what is the Kirchhoff's voltage law for this particular mesh 2? It is I2 double dash into Z2 plus I1 double dash plus I2 double dash into Z3. That should be equal to what? E2. So if you rearrange this, E2 should be equal to Z3 I1 double dash plus Z2 plus Z3 into I2 double dash. And if you solve equation 10 and 11, so we will get the values of I1 double dash as minus of Z3 E1 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1, and I2 double dash as minus of Z1 Z3 into E2 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1. Now you can, if you see this equation 8, 9 and equation 12 and 13, so we can simply say that if you add up equation 8 and equation 12, I mean this equation and this equation, I1 dash plus I1 double dash, that is nothing but it is an I1. So now you can see here, you got it as I1 was in this value. This was an I1, equation 3. So if you add up equation 8 and equation 12, that is nothing but equation 3. And that is nothing but we can say that I1 is equal to I1 dash plus I2 double dash. Similarly, if you add up equation 9 and equation 13, that is nothing but equation 4. This was an equation 4. And equation 4 was nothing but I2. So if you add up equation 9, it means I2 dash and equation 13, I2 double dash. So I2 dash plus I2 double dash is nothing but you can see in the equation number 15 as I2. So what we got it is I1 is equal to I1 dash plus I1 double dash, and I2 is nothing but I2 dash plus I2 double dash. What was I1 dash? I1 dash and I2 dash was where when the one source is removed. Similarly, I1 double dash and I2 double dash is nothing but what? When the another source in another mesh was removed. So this is nothing but a superposition theorem. I just want to repeat the statement for the superposition theorem using, if you see the equation 14 and 15, once again I'm repeating the statement for the superposition theorem. In any linear network containing linear impedance and energy sources, the current in any element is the vector sum of the currents that is separately caused. The current in any element is the vector sum of the currents that are separately caused in that element if each source of EMF were considered separately. So this is how they are saying the vector sum of the currents. It's the vector sum of the currents that are separately caused. See, this I1 dash is caused because we have removed the E2. This I1 double dash is there, the current in the mesh, because of E1 is removed. So this is the total current where the current are caused separately. The current in any element is the vector sum of the currents that are separately caused in that element if each source of EMF are considered separately. So once again, I'm repeating this. This is called superposition theorem. So I1, if you prove it as an I1 dash plus I1 double dash, or I2 is equal to I2 dash plus I2 double dash, then we can say that the superposition theorem is true. Well, let's have a practical example applying the superposition theorem to any of the linear network and find out the values. So let's take this as an example. Okay, so this is a circuit where which we have taken two sources, and here we are finding out the values of total current like I1 dash and I1 double dash. It means we are finding out what is I1, what is I2, what is I3 by summing up all the different branches when removing the one source and then another source. So we can see this is a voltage value of 120 voltage. This is a 6 ohm resistance, 3 ohm resistance, 2 ohm resistance, 4 ohm resistance. And the current in this particular branch we have taken as an I1, here I2, this is I3, this is I4, and this is a source which having a current value of 12 amps. Okay. Then this can be called as an application of the superposition theorem, where it is used to calculate the branch current. Now we need to find out what is the value of I1, I2, I3, I4 using the superposition theorem. So previously we studied that it's nothing but a vector sum of the current caused separately, saying I1 was equal to I1 dash plus I1 double dash. So that's the same principle we need to apply onto this particular circuit and find out the current in each of the branches. So how we will begin? By calculating the branch current caused by the voltage source of 120 volt. Let's begin from this side. By substituting the idle current with an open circuit, we deactivate the current circuit. So if we label these 2 points as the terminals A and B, we need to open this particular. This is what the condition first we have studied for the superposition. By open circuit, so we have to remove this particular 2 points and make it as an open. Then we need to find out idle current with an open circuit by deactivating the current source. So we have to remove this current source. So this will be the new circuit. See here we have kept as an open current circuit. This can be called an open current circuit. We have removed this current source. Okay. So the circuit is like voltage source is 120 ohm, R1, R2, R3, R4. The I1, I2, I3, I4 are the branch currents. Now to calculate the branch current, the node voltage across the 3 ohm resistor must be known. Okay, so we have labeled this as a node V1 and this as a V2. So now we need to find out the V1. So how applying the node voltage, previously we have seen how we can get the value of V1. So this should be what? This is in, suppose we say this is in V. So to find out the voltage, node voltage for this particular branch, the formula according to the previous topic, it's nothing but V1 minus, if this is a V2, so V1 minus V2 divided by R, isn't it? Similarly, R1, similarly V1 divided by R2, plus this should be what? V1, okay, divided by this 2, because we have kept this as an open, these 2 are in series. So the last will be V1 by 2 plus 4. So the equation comes like V1 by 120 by 6. Here you can see that, plus V1 by 3, then plus V1 by 2 plus 4, and this comes like a 0. By applying the Kirchhoff's voltage law, please, I'm just going back. If you could not remember, see, this is how we have done it. Applying node 1 and node 2 and node 3. So this was a node 1. So this is how it has come. For the node 3, node 2, this one, node 3, this one. So using the same nodal analysis to this particular circuit, we can have the equation in this form. And if you solve this, we'll get V1 as an 30 voltage. Because summation of all the voltage should be equal to 0. This is what the Kirchhoff's voltage law says that. So if you solve this, we'll get V1 is equal to 30 voltage. Now we will find out the equation for the each branches. I mean I1, I2, I3 and I4. So what is I1? Now, so when we have removed this current source and made it as an open current source, the branches in each, the current in the each branches, we label it as an I1 dash, I2 dash, I3 dash and I4 dash. As we got the node voltage V1, we can easily find out what is the value of I1 dash, I2 dash, I3 dash and I4 dash. So this is how it comes like. So what is I1? If you see that, what is I1? So I1 is nothing but this 120 minus what is the V1 voltage? This is 30. So V by R. So 120 by 30 divided by 6. So that comes 15 amps. Similarly, what is I2? This is an I2. So I2 is nothing but voltage by resistance. So what is V1? V1 is 30. 30 by 3 is how much? 10 amps. Similarly, what is I3 now? I3 is nothing but V1. V1 is how much? 30. 30 divided by, because if you have kept these two terminals in open, this resistance R3 and R4 are coming into series. So V1 divided by 2 plus 4. So V1 is 30. 30 divided by 2 plus 4 is 6. So 30 divided by 6 is nothing but 5 amps. So this is how we get the value of I1 as in 15 amps, I2 is in 10 amps, and I3 and I4 will get the same values as in 5 amps. If you find out, because both resistance, this I4 and I3 will be same because these two resistance are in series. So the same current value will be flowing through this particular R3 resistance as well as an R4. So we can say that I3 dash is equal to I4 dash, which is coming as in 5 amps. So this is how we have done it. Okay. Now in order to calculate the current caused by the current source, we deactivate the idle voltage source with a short circuit. Okay. Now this can be called as an open voltage source. Earlier it was called as an open current source. We have removed the current source here, and this is called as an open current source. Now keeping this particular current source, we will remove this voltage source. So then that can be called as an open voltage source. Got it? So this is, we have removed this particular voltage, and then this can be called as an idle voltage source or open voltage source, and considering it is current source. So again the same R1, R2, R3, R4 resistance, and the current in each branches we label it as an I1 double dash, I2 double dash, this is I3 double dash, I4 double dash. Okay, now we will find out the value of each current in the branches. So to determine the branch current, solve the node voltage across 3 ohm and 4 ohm. So we need to find out 3 ohm and 4 ohm. It means node voltage is what? Here we have taken as in this node voltage, this one and this one. Let us say that this is V3 and this is V4. Okay. So how it comes? It comes like V3 by 3 plus, this is V3, right? So this is node voltage V3. So to find out the current over here, it is nothing but V3 by 6 on this particular branch, and using the node analysis. Similarly on this branch, V3 by 3. Okay. On this branch, this comes like this, because there is a current source, these two resistances are not in series with each other. Earlier we have done these two resistance are in series with each other. But here, how it will come, like we said that here we have assigned the node voltage here as in V3 and here as in V4. So it comes like V3 minus V4 by 2. Then, so the total summation if I do, it is nothing but V3 by 6 plus V3 by 3 plus V3 minus V4 by 2, and this should be equal to 0. Please follow this particular equation. Similarly, applying or analyzing the node voltage at this particular assigned V4 value. So this is another node where we said that the voltage as assigned is in V4. So to find out V4, how it comes like, so V4 for this particular branch, it is quite simple, V4 by 4. And here, this is nothing but V4 minus V3 by 2. Please see this circuit diagram. This is node voltage assigned as a V4, and we are finding out the current over here. That comes like V4 minus V3 divided by 2, V4 divided by 4, and this is the current value straight as in 12 amp. So how the equation comes like V4 minus V3 by 2 plus V4 divided by 4 plus 12 is the amps should be equal to 0. So these are the two equations. These are the two equations. So if you solve these two equations, we can get the two node voltages V3 and V4 as V3 as an minus 12 voltage and V4 as minus 24. Actually, V4 you get it as in 2 into V3. So 2 into V3 is 2 into minus 12 is 24. So V3 we will get as in 12 minus 12 volt, and V4 we will get as in minus 24 volt. Now it's quite simple to find out the value of I1 double dash from this diagram. I1 double dash, I2 double dash, I3 double dash, and I4 double dash as we have found out here. So that comes like, if you see here, this is I1 double dash is nothing but, because this we labeled as in V3 and this is in V4. So V3 by 6, I2 double dash will be V3 by 3, I3 double dash is nothing but, this is V3 minus V4 by 2, and similarly I4 double dash will be V4 by 2. So if you see this and put the values of V3 and V4, you'll get it as an I1 double dash as I have explained this by the circuit diagram. So this comes like I1 double dash is equal to 2 amps, I2 double dash is equal to minus 4 amps, I3 double dash is equal to 6 amps, I4 double dash is equal to minus 6 amps. Now we need to find out the actual current. So actual current I1 should be equal to I1 dash plus I1 double dash. I2 should be equal to I2 dash plus I2 double dash, and so on and so forth. So if you add up actual current of the circuit, adding the currents due to both the currents and the voltage source, then we will get as an I1 is equal to 17 amp, I2 is equal to 6 amp, I3 is equal to 11 amp, and I4 is equal to minus 1 amp. So to find out the current in this particular each branches I1, I2, I3, I4, what we did is we have kept this as an open current source, and we have found out the new currents in the each branches as an I1 dash, I2 dash, I3 dash, I4 dash. Then for the second part, we have removed this voltage source, saying that it's an open voltage source. Okay, and then we have found out the I1 double dash, I2 double dash, I3 double dash, and I4 double dash. So according to the superposition theorem, it should be the vector sum of the current which is caused separately. Then we said that I1 was equal to I1 dash plus I1 double dash, I2 was equal to I2 dash plus I2 double dash. So in that manner, we have found out by using the superposition to that particular given network circuit, we found out the value of each current in each particular asked branch. So we found out the value of I1, I2, I3, and I4. So this was all about superposition theorem. Now Thevenin's theorem. The next theorem is called as a Thevenin's theorem. The statement for Thevenin's theorem is